Right now I'm excited to get to show you about terminal voltage because this is something that a lot of people just really don't understand. I can sum it up really simply. I've got a nice Duracell battery, fairly fresh, and when I connect it to this electric motor, to the two terminals in the back, it's going to cause the motor to turn and the fan to spin. And just listen to how that sounds. Got that? Now that's a 9-volt battery. Here's another 9-volt battery, and I connect that to the motor. You can hear it's really not spinning nearly as fast. Now why is that? Well, you might say that it's the voltage is different between the two batteries. But if I take my voltmeter here, and I have one of the plugs plugged into my voltage terminal, the other to the common ground. And if I use that, I turn my dial to 20 volts DC. And if I connect it to the two leads on the battery, what I end up getting for a measurement for the Duracell is 9.18 volts. Now let's take a look at the EverReady. Now the EverReady, if I plug it in, I actually get 9.13 volts. Now you might say, oh, that one's more. Not much though. That's not actually what's happening that's causing the difference. Both of these batteries read 9 volts when there's no load on it, when there's no current being drawn. But as soon as current is being drawn from the battery, there's internal resistance in these batteries that will lower the terminal voltage so that the actual output of this 9-volt battery is significantly different than the output from this battery, even though they have the same voltage. How can we quantify this idea of the terminal voltage being different than what the battery is actually rated at? Well, that's where our formula comes in. So in your notes, take out a nice clean sheet of paper, draw a couple pictures of batteries, and let's start with this statement. Both batteries measured 9 volts when no current is flowing. So why did they perform so differently? Well, in the video clip that we just watched, I used the term internal resistance. So now that you're caught up, if you're not caught up, push pause. First, we're going to talk about what is this 9 volts anyways? The 9-volt battery doesn't actually supply 9 volts of electricity when hooked up to a circuit. There's always going to be some internal resistance in the battery. That rated voltage is often referred to as the EMF. Now, this is a term that goes way back when they would actually be describing electricity as a force. Instead, we are describing electricity in terms of energy, but they would have called this the electromotive force. Hence the EMF. And the symbol for that is this stylized, italicized capital E. Okay? So these batteries are rated at 9 volts, but they don't actually deliver 9 volts because of the internal resistance. The voltage actually changes depending upon what's hooked up to it. So how do we account for that? Well, we can find the actual voltage when under a load is equal to the rated voltage minus the voltage drop that occurs within the battery or power supply itself. Now, that voltage drop is going to depend upon the current that's flowing in the circuit and lowercase r. That lowercase r is the internal resistance of the power supply. So let's take a moment and define what each one of these variables are, right underneath. So V. V is known as the terminal voltage. That funny looking E is the EMF, which I prefer to use the term the rated voltage. What it would be with no load on it. I stands for current, and obviously that changes depending on how the circuit is hooked up. And now all of a sudden you're seeing, oh, this could be different depending on what it's hooked up to every single problem. Yep. And lastly, this lowercase r. Lowercase r stands for internal resistance. And yes, it's a lowercase. When we draw it in a circuit, what we would draw is a power supply, resistance R of our circuit. Now this could be multiple resistors. I'm just going to represent that with just one resistor for now. And then as I complete the circuit, internal resistance is drawn with the battery or power supply. And we would use the symbol lowercase r. It would also have an EMF would be the rating of the power supply or battery. Now, in order to, actually, you know what? In order to get a visual, let's picture this left side as a battery. So let's say this is a AA battery this time, you know, those little cylindrical ones. It's got a positive and a negative terminal on it. The internal resistance is actually inside the battery. And the terminal voltage is the voltage you get at the terminals. The terminals are literally like the connections on the battery. So from A to B, often you might see it written as A to B or X to Z, whatever. Actually, I guess it would be X to Y. But the point is, the voltage drop that occurs because of the internal resistance actually occurs at the power supply. And the terminal voltage would be if you were to connect to each of the terminals on the battery when hooked up to a circuit. That's what the word terminal voltage means. It doesn't mean like it's dying. It's not terminal. It's the terminals on a battery. All right. I'm going to take a break. I can see how terminal voltage affects the output by looking at a battery. This is a 6-volt lantern battery and a light bulb. Now that light bulb is actually rated at 3 watts, and it's actually designed to be used with a 6-volt power supply like we have here. If I take my multimeter, not a battery tester, a multimeter that is set up to measure the voltage drop across these two terminals, when there's no load on it, when no current is flowing, it's going to have a voltage of 6.06 volts. Okay? But once current starts flowing, and I can connect the light bulb by these wires. Current is flowing, and it's obvious because when hooking up a voltmeter to measure the voltage drop across a resistor, I have to hook that up parallel to the circuit. So I'm going to take my black wire, my ground wire, and connect it to one end of the light bulb. Whoop. My red wire to the other end. Let's see what we get for a voltage drop. Now this is reading a voltage drop of only 3.84 volts. Now the only thing connected to this are these wires, which I'm going to assume have a resistance of 0, and the light bulb. But it went from 6 volts to to now only delivering 3.86. So where is that energy? See it? Yeah, it's in here. Some of that energy is going into heating up the battery. And in fact, I don't actually get 6 volts out of this battery. We're only getting 3.84 volts when this current is being drawn from the battery. All right. So now you're asking the question, what is the internal resistance of that 6-volt battery? I'm glad you asked. Let's figure it out. In your notes, go ahead and write this question down. What is the internal resistance, lowercase r, of the 6-volt battery? And while you're writing that out, I'm going to go ahead and draw our circuit. We have our battery, which was rated at 6.06 volts. I connected that to one side of a light bulb, which I'm going to represent as just a common resistor. We then had current flow through the ammeter to measure current before going back to the power supply or the battery. Now that had internal resistance, little r. Now I hooked up a voltmeter in parallel with that resistor so I could measure the voltage drop across that R. And what I found that to be was 3.84 volts. It fluctuated slightly, but it's pretty much 3.84 volts. Now that would be the same as the terminal voltage that you get out of the battery when current is flowing. Because again, let's picture this whole side is my battery. So that internal resistance is occurring inside the battery. So if I look at my relationship, which is V equals EMF minus IR, just for today, I'm going to go ahead and just plug in my values right below. So the voltage you actually get out, 3.84, equals 6.06 minus the current that is drawn times the internal resistance. I do a wee bit of algebra. I get negative 2.22 equals negative 0.33 R. I get R all alone. And I get an internal resistance of approximately 6.7 ohms. Now that's going to change over the lifetime of the battery. When the battery, quote, dies, you can often still get the full 6-volt reading when there's no load. But then as soon as current starts to flow, the internal resistance drops that to near zero. So it's the internal resistance of a battery that changes as it starts to use up its energy. Think you got this? Good. I think you do too. Thanks for hanging in there.